I want to do, I want to talk to you about singularities. Of course, in the last lecture, we had seen various types of singularities, and we had also seen the characterizations for those singularities in terms of uh, the behavior of the function around that point, right? Okay, so primarily the key difference between uh, removable and singularities which are not removable were that removable for removable singularity the function was bounded in a neighborhood around that point, and for the singularities which are not removable the function was unbounded. And now among the functions which are unbounded we can have two kind of possibilities, like that in the sense that whenever we approach our point of interest, the mod of f of z will have, since it's going to be unbounded, so it's natural to expect that mod of f of z might go to plus infinity. So if that happens, then we get something called polar singularity. And if near the point z, the functional values are random in the sense it might go to, means like it might go to plus infinity and it might also might not go to plus infinity. So let's say we have two sequences for which image of both these sequences are converging to the point of interest, and one of them, for one of them the functional value is remaining bounded, and for the other one the functional value is going to infinity. Okay, so if that's the case, then we get something called essential singularity. Okay, so in fact, for essential singularity, it's not just a matter of one sequence being bounded and one sequence diverging to plus infinity uh, in absolute value. We even have a stronger theorem which is called the Casarotti-Weierstrass theorem. So what does Casarotti-Weierstrass theorem tell us? It tells us that if I take any alpha to be an essential singularity, okay, an essential singularity, suppose I have this, then you take any, no matter how small neighborhood you want to take of alpha, then for any r positive, the set f of b alpha r minus alpha, this set is actually dense in C. Okay, so that means what? It says that you will be able to find sequences in this particular ball. So no matter how small ball you want to take, you will get sequences converging to alpha such that the functional values can go to any point that you wish in the complex plane. Okay. So we were seeing that one sequence will remain bounded, another sequence will diverge to plus infinity. Whereas here what we see is that no matter what complex number you choose, you will always be able to find you will always be able to find sequences which are converging to alpha such that the image of that particular sequence will go to that particular complex number. Okay, so this is very powerful statement, and that shows that actually essential singularities, like we were discussing, that if I have a removable singularity around alpha, it has a definite limit, which is f of alpha, because means the function can be actually made continuous there. Around around a pole, the function has a definitive behavior that it will always go to mod of f of z will always go to plus infinity as mod z tends to alpha, as z tends to alpha. But here, in case of essential singularity, what we see is that you can even approach any point that you like. Okay, so is the statement clear of Casarotti-Weierstrass? Yeah.
Yes, sir.
Okay, so now to show that some set is dense, you probably have seen already by in topology, what you need to do, that it needs to intersect all kinds of open balls. right? So we show that f b alpha r minus alpha intersects any ball b a delta in C. Okay, so it intersects any ball b a delta in C. Okay, so this is what I need to prove. Fine. So do you agree that if I can prove this, then we will be done? Yeah.
Yes, sir.
Okay, fine. So let's do that. Now, suppose if this is not true. So suppose this is not true. It's not true. Let be a delta intersection f of b alpha r minus alpha is equal to empty for some a in C delta positive. So suppose I have this. Okay. Now I need to get a contradiction. Okay. So this implies what? If this ball does not intersect the image, that means my function is strict, means like it is not only away from A, but it's away from A with a distance delta at least. Okay. So that is mod of f of z minus a is strictly bigger than delta, which is positive, for all z in this ball b alpha r minus alpha. Okay, so this is what we have. Okay, fine. Now this guy is this is something, this is a function which is becoming, as I can see, in absolute value this is bigger than delta. So that means this function is staying away from 0. This function f of z minus a, this is staying away from 0, right? So if that happens, then what I can say, I can, if I take the reciprocal, then that function will be actually a holomorphic function. Hence, hence g of z, which I can define by 1 over f of z minus a, this is holomorphic on b alpha r minus alpha. Okay, that's good. And now what I can also observe is that, you see, this g would have been holomorphic just if f of z minus a would have been non-zero. That would have been good enough to say that g is holomorphic. But I have something much more than that. I have that mod of f of z minus a is bigger than delta, which is bigger than 0. So that in turn gives us a bound for my function g. So what is that bound? So we get
One
on,
over delta.
very good, b alpha r minus alpha, we have mod of g of z is actually less than 1 over delta. Now that's a finite quantity because my delta was positive, so this is a finite quantity. So therefore, what do I see? For this function g, which is defined in a deleted neighborhood of alpha, I see that this function is bounded. So therefore, what can I say about alpha for the function g? Can you say something?
Removable singularity.
Very good. So alpha is a removable singularity for g. Singularity for g. Very nice. So there exists a holomorphic function h such that h on b alpha r such that h of z is equal to 1 upon f of z minus a, which is same as g of z, on b alpha r minus alpha. Fine. So therefore, what is my f? So this implies f of z is equal to a plus 1 over h of z on b alpha r minus alpha, right? I can get that. Okay, fine. Now I am going to get to some contradiction over here. Okay, so I will make two choices. So if h of alpha is not equal to 0, then we get that. So if h of alpha is not equal to 0, then again this quantity is going to be, something which is non-zero. So therefore, like, this, the denominator is non-zero. So when I take a reciprocal of that, that's going to remain bounded. So hence we get f is bounded around alpha. Hence alpha is a removable singularity. But that's a contradiction, because I have started saying that alpha is um,
Essential.
essential. So therefore, this case is not possible. So h of alpha cannot be non-zero. So therefore, what do I have? I must have. So h of alpha must be equal to 0. But if h of alpha is equal to 0, then what do I see? I see that. So if,
Alpha is pole.
yeah, exactly. If h of alpha is 0, then we see that because here I'm going to get h times, so like you can write, then we see that f of z is equal to a times hz plus 1 divided by hz. Of course, if h of alpha is 0, you can see clearly that the numerator is non-zero. So because that's, there is a 1 added to it, then we see that on b alpha r minus alpha, and numerator does not vanish on alpha. Hence alpha is a polar singularity. But this is again contradiction, right? Because again we had assumed that because we are given that alpha is a is an essential singularity, so this is not also possible. So that means this, so in both the cases we are getting contradiction. So this gives us the desired result. Okay, so we assume that let's say the image is not dense, so it's not intersecting some ball, and then we got some contradiction, okay, in whatever the case that you can think of. So therefore, what we see is that if we have an essential singularity, then we have a powerful theorem which says that actually the image is dense in whole of C. Okay, so this is very special. So it's not only I can like I can find two sequences, one remaining bounded, whose functional values, one for one of them remaining bounded, another one going to plus infinity. Rather, I can approach any point. Okay, so I can find sequences converging to alpha, different sequences, and the images are going to go to different points. Okay, so this is what we get. Fine. So that's about the Casaretti-Weierstrass theorem. So this extends our previous observation about the uh, essential singularity. Okay, fine. So now what we are going to do, like I told you in the last class, when we had holomorphic functions, we had power series expansion around a point. Now, if I take a function which is having a singularity at some point, then what we would like to do, we would like to have a similar kind of expansion. Okay, and this expansion will also tell us in return that what kind of singularities do we have. Okay, so for example, you can imagine, because if for instance my point is a removable singularity, then what happens then, means that means I can actually make the function to be holomorphic at that point, and all I need to change is the functional value at alpha. I don't have to change anything there. So and so therefore, for example, if the function becomes holomorphic, it will have a power series expansion. Okay, so in case of removable singularity, it's very natural. And on the other hand, you have also seen that in the last class that if I have a polar singularity, then we noticed that the function could be actually written as a holomorphic function divided by z minus alpha power m for some m positive. Okay. And that m was the order of the pole at that particular point. If that is the case, then again the numerator I can expand into a power series, and then in the denominator I have just, let's say, z minus alpha power m. So you can, formally at the formal level you can think of dividing it, and then you can think of exactly like formal power series, expansion of the form where you are also getting negative exponents. Okay, so this is what uh, LoRa expansion is all about. Okay, so of course we also need to understand how, if at all, we can write down a LoRa expansion around any point of singularity. Then, for example, if the point of singularity is an essential singularity, then what kind of, like, how will the LoRa expansion look like? So you can just, for your means, just for an example, you can try to imagine. I gave you this example of e power 1 over z, and that was an example where z equal to 0 was an essential singularity, right? Now e power a, you know what is the expansion of e power z, you know what is its power series expansion, which is valid in whole of c. Then automatically, if you just, again, like I was telling you, formally, if you try to see what is e power 1 over z, so you would like to write like 1 plus 1 over z plus 1 by 2 factorial into 1 over z square plus 1 by 3 factorial into 1 by z cube, and so on and so forth. So if you think of if you think of e power 1 over z in terms of that, at least formally, then you seem to be getting a LoRa expansion or some expansion where there are infinitely many negative exponents. Okay. So in this topic of LoRa expansion, what we will see is effectively that. So when we will have removable singularity, we are just going to get an expansion which will be the same as power series expansion. If in case of polar singularity, we are going to get a LoRa expansion where there will be only finitely many negative exponents of z minus alpha. And if my alpha is an essential singularity, then I will have a LoRa expansion. So of course there could be terms with positive exponent, but necessarily there will be infinitely many terms with negative exponent of z minus alpha. Okay, so is this clear what I'm trying to say?
Yes, sir.
Yeah. Okay, so let us now start this concept of LoRa expansion. Okay, so let's see. Okay, fine. Now here I will just since I'll be talking about LoRa expansion, so I also need to talk about, convergence of LoRa expansion and all that. So I'm going to start by taking the following definition of convergence for two-sided series. Okay, so that's my definition which I am going to start with. So let Zn, so here n is indexed over integers, be a double-sided sequence. Okay, we say summation n in zn converge absolutely is absolutely convergent if both summation n bigger than or equal to 0 zn and n less than or equal to minus 1 zn, or this one you can also write as, okay, it doesn't matter, or this you can write as n bigger than or equal to 1 z minus n are absolutely convergent. Okay, so if that happens, then we say that summation n in zn converges, and in that case we have summation n in z. Zn is n bigger than or equal to 0, Zn plus n bigger than or equal to 1, z minus n. Okay, so this is what how I am going to treat convergence of double-sided series. Okay, so it's more like I do not know if I have told you this or not, but generally you should kind of keep it in mind. Keep infinite series in mind in analogy with improper integrals. Okay, so when you have improper integrals where you have problems in two ends, then you take some in between points and you say that from that particular point, like on both sides the improper integral should converge, kind of that. So similarly here I said, okay, fine, I start one series I take from n bigger than or equal to 0, one series I take from n less than or equal to minus 1, and then my in both the cases my series should converge. Okay, so that's the definition for double-sided convergence of double-sided infinite series. And similarly, if I have a sequence of function, so similarly if fn, let's say n is indexed over z, is a sequence of functions on a set x, we say fn n in z is normally summable. Okay, so the normal convergence, notion of normal convergence we had used in case of power series. Normally summable if the two sequences fn n bigger than or equal to 0, and if, let's say, and let me write minus n bigger than or equal to 1 are normally summable. Okay, so this is what I have. Okay, great. So now I'm going to start with notion of former Lorentz series, like exactly like power series. So exactly we are going to begin with formal Laura series first, and then we will talk about where it can converge. And once we understand that, then we will talk about general Laura expansion of means functions which are having singularity, isolated singularity at a point. Okay, so isolated singularity means we have seen that there will be a neighborhood where the function will be holomorphic except for that particular point. Okay, so let's begin with formal Laura series. So a formal Laura series is an expression, I can say, of the form summation n in z a n x power n. Okay, and where if you want x is a symbol or indeterminate and ans are complex numbers. Okay, so this is what we have. Now, once I have written down this formal Laura series, clearly we would be interested to talk about its convergence. And therefore, what we do is that we're going to consider the power series. Like here, I took two infinite series. I broke my infinite series, double-sided infinite series, into two parts. So here also I'm going to take power series out of this Laura series. Okay, so we consider two associated power series associated power series. So the one will be very obvious, namely power series summation n bigger than or equal to 0 a n x power n. So that's very natural. And for the other one, what I do, I so see for the other part, of course, the exponent of x is negative. Okay, but what I do is that I would like to see it as a power series. So for example, you can imagine like replacing 1 over x by y. Okay, and then thinking of the negative side, like the parts with having negative exponent also as a power series. Okay, so at this moment just treat it like that. Anyway, all these are symbols. So this one and the second one is n bigger than or equal to 1 a minus n x power n. Okay, so again I am taking, I could have written y, but it doesn't really matter, and I have this one. Okay, fine. And now what I do is the following. You see, I have already told you that in your head you can kind of imagine this the second power series as y power n, with the understanding that y is equal to 1 over x. Like you can think of this in this way. And so what happens if that, for example, if I say that this power series, let's say, converges for mod of y less than rho, then you can think of that, okay, so that means the actual series, if I take a minus n x power minus n bigger than equal to 1, then this guy is going to converge for 1 over x, 1 over x in absolute value less than rho. So that means for x in absolute value bigger than 1 over rho. Right? Is it clear what I'm trying to say?
Yes.
Okay. So it's just a matter of taking some reciprocals. Okay, fine. So therefore, what I do is the following. Instead of writing 1 over rho over here, what I do is the following. Let's see. So we write, or let rho 1 be the radius of convergence, of summation n bigger than or equal to 0 in x power n. So remember, here y is also a symbol, but I am telling you to think of y as 1 over x. Okay, but that's not like here, there is no meaning of 1 over x as such, so it's just a symbol anyway. So, or you can think of x inverse y as x inverse. So anyway, so rho 1 is the radius of convergence of this formal power series, I'm assuming. And for convenience, assume the radius of convergence of n bigger than equal to 1 a minus n y power n is 1 over rho 2. Okay? So your rho 2 could be 0 and infinity. I have already told you this, that whenever we take formal power series, we allow our radius of convergence to be 0 as well as to be plus infinity. So whatever is your power, means actual radius of convergence, you just write it as 1 over reciprocal of something. Okay, so I just write it as 1 over rho 2. So therefore, what I can say is that, therefore, the series summation n bigger than or equal to 0 n z power n is converges absolutely, even normally on compact subsets, normally on compact subsets of uh, mod z less than rho 1. Okay, so that much I can say for sure. And secondly, if I think of the other sum and the series summation n less than 0 let's say a n z power n, this guy means that is which is correspond to this guy is going to converges again absolutely and normally on compact subsets, normally on compact subsets of mod z bigger than rho 2. Okay, so is this clear? Yeah, do you all see this?
Yes, sir.
So if you are confused little bit with the last statement, so how you really should see this is that if mod of z is bigger than rho 2, then 1 over mod of z is less than 1 over rho 2. So when you think of substituting 1 over z over here, that's going to converge. Okay, so because this is precisely I have taken that this is the radius of convergence. Okay, so you can just do it like this and you will get it. Okay, and moreover, okay, so wherever I was having, if I have a power series which converges in certain disk, then it's going to be holomorphic, and going from y to x is just a matter of change of variable. Okay, so there is absolutely no change, and moreover I can say that if I, let's say I call this f2z, this one, if I define it to be summation n less than 0 a n z power n, then f2z is holomorphic for mod z bigger than root 2. Okay. So this one I can say, of course, how, if I want to take the derivative, how I should do it, because I can write, for example, f2 of z as some new function g of 1 over z, and then I can take the derivative. Okay, so let me do that since this part is slightly different from power series. So let me do that. Okay, so define for mod of u less than 1 over rho 2, define, okay, g of u by summation n bigger than 0 a minus n u power minus n. Okay, so that's the power series which I had over here. Okay, so I take that one and define this g, and clearly, so now this is just a power series, so clearly g is holomorphic. And not only that, I can also say what is g prime of u. So g prime of u is n bigger than 0 n a minus n u power n minus 1. Okay, now if mod of z is bigger than rho 2, then what I see is my f2 of z is nothing but actually g of 1 over z, because of course 1 over z is something which is non-zero, z is non-zero, so 1 over z makes sense. So f2 of z is g of 1 over z, and now if you just think of this is like a chain rule composition of two function, then hence I can say that f2 prime of z is nothing but minus 1 over z square g prime of 1 over z, just a chain rule. Okay, and what is g prime of 1 over z? So let us keep minus 1 over z square over here, and g prime I have just calculated over there. So this is summation n bigger than 0 n a minus n u power n minus 1. So therefore in place of u I should have 1 over z, so that is 1 over z power n minus 1, and therefore this one I can write as, let's just be a little bit careful, n bigger than 0 I can write minus n a minus n 1 over z power n plus 1. Fine. So this is nothing but, if I write in terms, not in terms of n positive but rather n negative, then this will be n negative n a n z power n minus 1. Okay, so exactly because I just need to replace n by minus n, then I get this one. Do you see this?
Yes, sir.
Okay, so therefore what I observed here is that, yes, is there any question? Okay, so here it was n plus 1, it became n minus 1 because I substituted minus n by n. Okay, so just matter of change of variable. So therefore I have this, and now here what I see is that my f of z was this, and this became my f prime of z. Okay, so therefore what I can see from here is that the derivative of the negative term on the negative exponent can also be obtained by differentiating term by term, right? Exactly, that is what we are seeing, isn't it? So we also get that um, f is f rather f2 is differentiable term by term for, of course, mod z bigger than rho 2. Is this clear to everybody? Yeah, we had seen term by term differentiation in case of power series, and here also we are going to have that. Okay, so if I just think of the negative part, so that's going to be differentiable, and I can get the derivative just by differentiating term by term. Fine, is this all right?
Yes, sir.
Yes, sir.
Okay, great. So now that I understand where each of these two are converging, so therefore let's see what do I really need to make sense of this LoRa series in a convergent form. So first of all, the power series, which is already the part of my LoRa series. So that one, the power series, the main power series converges for mod z less than rho 1. Okay, and the part with negative exponent, the negative part, so that one is going to converge for mod z bigger than rho 2. So something is convergent, some part is convergent for mod z less than rho 1, and some part is convergent for mod z bigger than rho 2. Of course, I have told you that to say that a doubly sided infinite series is convergent, I would like to have convergence of both of them simultaneously. Okay, so therefore what is the set where I can expect the LoRa series to be convergent? Tell me.
Sir, annulus row 2 row 1.
Very good. So therefore so to in fact have some non-empty set, we first assume, so now suppose rho 2 is less than rho 1, then we get that the sum is holomorphic on the annulus rho 2 less than mod z less than rho 1. Okay, and what is the derivative? With derivative summation n z n a n z power n minus 1. So this is precisely the derivative. Okay, with derivative this one. So here like in case of power series, our like open domain of convergence was an open disk, and in this particular case our open domain of for LoRa series, our open domain of convergence is going to be some annulus like this. Okay, so this is what we are going to have, and our in general, if LoRa series, if it converges somewhere, then it's going to converge on domains like this. Okay, so of course you may so happen, it means like it may so happen that for example your this particular power, sorry, so this particular power series, when I am taking this as a power series, it may so happen that this power series actually converges for whole of C, and therefore the radius of convergence becomes plus infinity, and therefore your rho 2 could be equal to 0. Okay, now if rho 2 is equal to 0, then tell me how does the annulus look like in that case? If for example rho 2 is 0, then what is effectively this annulus?
Disk
Disk.
with radius rho 1.
Not exactly the disk, slightly smaller than disk. Sorry?
Center and the circumstances are not included.
Yes, so that means it's a deleted neighborhood, right? So exactly this is what we are going to encounter when we talk about, like, expansion, LoRa expansion for a holomorphic function and having a singularity at a point alpha. Okay, so we already know there that the function is going to be holomorphic in, let's say, B alpha R minus alpha. So you can in fact imagine, that's what is my point, is that you can imagine deleted neighborhood as annulus, right? And we will see that we are going to have LoRa expansion of that kind. Okay, so in general, remember this, that LoRa expansions are convergent, or LoRa series, like exactly like power series were convergent in a disk, and here LoRa series are going to be convergent in annulus. Okay, so the uh, an open set where a LoRa series would be convergent would be of this form: mod of rho 2 less than mod z less than rho 1. Of course you can change the center. Here the center I am working at 0, but that does not really matter. You can just change it to any center, like you could have rho 2 less than mod of z minus a less than rho 1. Okay, so that is really not so important, but we are going to have that. Okay, so effectively what I am getting is that if I start with a formal LoRa series, then it's going to define a holomorphic function on this annulus. So let's say this is my 0. So up to this is rho 2, and up to this is rho 1. Then the LoRa series is going to be holomorphic in this range. Of course, if my rho 2 is bigger than rho 1, then there is no hope. Then it's going to be an empty set. But if my rho 2 is less than rho 1, then we are going to have, we are going to get convergence of LoRa series in set like that. Okay, and exactly like in case of power series, here also you can actually express the coefficients in terms of integral. Okay, so note that if fz is equal to summation n in z a n z power n on rho 2 less than mod z less than rho 1, then uh, what I can say is that an is uh, 1 over 2 pi I integral over gamma r. I will tell you what is gamma r is: f of z divided by z to the power n plus 1. Okay, where rho 2 is less than capital R less than rho 1, and gamma r is denotes r e power I theta. So this is the path which is gamma r, and then you can say your an is like this. Okay, so an is given by this particular thing. Okay, now this is nothing difficult, because if your fz is like this, you can just imagine what would be fz divided by z power n plus 1. So fz divided by z plus z to the power n plus 1 is going to be, anyway, remember I am in an annulus, so z is not equal to 0. So this will just be a n z power, sorry, let me write it as m is better. So many n's are there. So this will be a n z power, let's say n minus m minus 1, and of course the convergence is normal on compact subsets of rho 2 less than mod z less than rho 1. And once I have that, I can integrate. So 1 over 2 pi I integral of f divided fz divided by z minus z power m plus 1 over gamma r. This is 1 over 2 pi I summation n over z a n. uh, I need to integrate also, integrate over gamma r a n z to the power n minus m minus 1. And since I already have normal convergence and therefore uniform convergence, I can interchange the integral and summation. So a n comes out. I can integrate over gamma r z to the power n minus m minus 1. And this one we have already seen so many times. So over gamma r z to the power n minus m minus 1. Tell me, what is this integral?
0 or 1 upon 2 pi I. Sorry, 0
Zero,
or 2 pi I.
right? Yeah. So when it is 0 and when it is 2 pi I?
N is not equals to uh,
When is it 2 pi I? First tell me that. That will be easier to say.
N equals to M.
Yeah. So if n equal to m, and 0 when? If?
N not equals to M.
Absolutely. So therefore, in this integral, we know this. This we know. We know this already. So this integral, if you calculate, which term is going to come out? It's going to come out only am, right? So therefore, 1 over 2 pi I gamma r f of z divided by z power m plus 1 is 1 over 2 pi I into am into 2 pi I, which is am. Right. So exactly like in case of power series, I have a similar looking formula. Okay. So this is exactly that we have. Okay. Now, like I told you, if we consider a power series, a LoRa series f of z. So for example, just a small remark which I have mentioned already, that if we take f of z is defined by n in z a n z minus a power n for some a in c, then this defines a holomorphic function on rho 2 less than mod z minus a less than rho 1. This I have already said. So okay. So now, of course, in power series theory, we had seen that if I take a formal power series with positive radius of convergence, that defines a holomorphic function on the open disk of convergence. And similarly here, of course, we have seen that if I start with a formal LoRa series, then it's going to define a holomorphic function on an annulus like this. Okay, so of course, depending on the center, the means whatever you want to take, let's say LoRa series around a point, then accordingly it's going to be converging in an annulus around A. Okay, so or in a ring around A, something of that kind. Okay, so now what we had shown in case of power series also is that, like I said, any holomorphic function we're having power series expansion. Okay, and this time what we are going to see is that if I have, for example, uh, a any holomorphic function which is any function which is holomorphic in an annulus, then it will have a LoRa expansion. Okay, so in case of power series theory, we saw if I have a holomorphic function, let's say at some point, so that means it's holomorphic in a ball, then there is a power series expansion. Now I am starting with a function which is holomorphic in annulus, then I will be able to show that this has a LoRa expansion in that very annulus. Okay, so now I go to the theorem that any holomorphic function f of z in an annulus. So again, here I am going to, for simplicity, I am going to keep my center to be 0. Okay, but because it's just going to make my writing easier, but you can just have it at any point of at any point. Okay, so or maybe I can do it for your convenience. I can do it um, perhaps at any center, but yeah, this is not going to matter much. Okay, so let's do it that way. Just a second. Yeah, I can perhaps do it by taking any arbitrary center. Let us see. Annulus rho 2 less than mod of z minus a less than rho 1 uh, has a LoRa expansion. There. Okay, so like exactly when you think of a holomorphic function at a point, so the function becomes by definition is holomorphic in a disk. So you get a power, and then you got a power series expansion. Here I am starting with a holomorphic function in an annulus, and I want to get a LoRa expansion in that annulus. Okay, so how do I prove that? Okay, so for that, recall what did we do in case of power series. So I want to give a proof of this fact. Now, what did I do for a power series? I started with the Cauchy integral formula, if you remember, and then at any point alpha, I wrote down what is f of alpha in terms of Cauchy integral formula, and then what we had, we uh, once we had this Cauchy integral formula, there was this 1 upon z minus alpha inside, which I expanded, and thereby we got an expansion. Okay, so here also we are going to do a similar thing. Now all I need effectively is a analog of Cauchy integral formula. Okay, so an analogous expression which I am going to need. Okay, so what I am going to do here is the following. Okay, so for instance, I have this one. So let me see what I am going to do. So here, okay, so I take R1 and R2 positive such that, okay, so let alpha belongs to this set rho 2 less than mod z minus a less than rho 1. So I'm taking alpha from this set, and I need to show that f of alpha looks like summation an alpha minus a power n, where n varies over set of integers. That is what I need to do. And for this, we need to have an expansion, analogous expansion of the Cauchy integral formula. So what do I want to prove here? So we show that for if I take any, so if you remember when I took the Cauchy integral formula, I was taking a circle which was completely inside the ball, open ball, where the function is holomorphic. So here I am going to take similarly two circles. So of course my this is my annulus where the function is holomorphic, but I'm going to take two more circles over there. So how am I going to take them? So let me draw some picture. So let's say this is my A, and then let's say this is the actual annulus. Okay, and then what I propose is that I take another some two more circles like these ones. Okay, so one is slightly bigger, one is slightly smaller, and both of them are in between this row 1 and row 2. Okay, so that means what I do is that we show for uh, row 2 less than R2, which is less than mod of alpha minus A, less than R1 less than row 1, f of alpha is equal to 1 over 2 pi I integral over a plus gamma R1 f of z divided by z minus alpha minus 1 over 2 pi I a plus gamma R2 f of z divided by z minus alpha. So remember, this one is row 2, this one is R2, this one is R1, and this one is row 1. Okay, so this is what the picture looks like, and what I have is this one. Okay, so exactly in case of Cauchy integral formula, I did not have these two terms. I just had mod of alpha minus a is less than R1 less than rho 1, and analogously I did not have this term in case of Cauchy integral formula. So here, now that I am in annulus, I need to somehow nullify the effect of uh, this inner ball where the function is not holomorphic. So therefore I need to subtract this integral here. So is this clear what I need? Yeah, if you go back to the power series expansion theorem, you will see that exactly I started means we had this Cauchy integral formula which we had proved, and using that we got the power series expansion, right? Yes or
Yes,
no?
sir. Yes,
Yes.
sir.
Here also I am just going to have a similar thing, except that it's not exactly the Cauchy integral formula. Here I have a correction term. Okay, so how to remember this? Like for example, as I said, if you don't have this, you don't have this. So exactly like, so this is going to come for contribution coming from, as I said, the inner disk, which is missing in the annulus. Okay, fine. So that's good. Now, how did I means like how did we prove Cauchy integral formula? So the proof of Cauchy integral formula was quite easy. We had considered this function gz, which was equal to fz minus f alpha divided by z minus alpha for z not equal to alpha, and f prime alpha for z equal to alpha, and then we had just integrated. Okay, and thereby we got the Cauchy integral formula. So here also we are going to do similar thing. Okay, so let's see. Only thing is that when we were taking integrals, like in case of holomorphic functions over closed curves, we could say directly that those integrals are zero. But here we need to be slightly careful. Okay, so let us see what we can do. So, for example, uh, because my function is not holomorphic in the whole, like here in case it's not holomorphic in the whole ball, right? So there are certain portions, like I was telling you, this portion where the function is not holomorphic. So therefore what I do is that consider g of z equal to f of z minus f of alpha divided by z minus alpha if z is not equal to alpha, and f prime alpha if z is equal to alpha. Okay, now my goal is to show get the formula, of course, that is fine. So for that, what we show is that we show that integral of g over a plus gamma r1 is same as integral over g over a plus gamma r2. Okay, so once we have that, we will see how we are going to get the formula. So that's going to be very easy. Okay, so that's not going to be a problem. So let me quickly, now that I have 15 minutes time, let me quickly do this. So I need to show that these two integrals are the same. Okay, so how do I show these two integrals are the same? So let us observe the following. So let's again draw the same picture, or let me just copy this one. Okay, I have this picture. You can enlarge it a bit. Okay, and now, of course, I need to say this one. So here, what I do is that I divide this area into several sub areas. Okay, so this integral I break into several sub integrals of in the following way. Okay, so just try to understand what I'm trying to do over here. I'm going to go in this way, go in this way, and then come in this way, and then I'm going to again break this in this way, come back this way, similarly like this, like this, like this, like this. Okay, so I'm going to consider integrals in this kind of fashion. Okay, and similarly you can continue doing this. So you understand what I'm going to do. I'm going to I have to take these two integrals to be equal. So of course my aim will be to show that we show that integral of g over a plus gamma r1 minus integral of g a plus gamma r2 is equal to 0. Okay, and this a plus gamma r2 with a minus, that is same as taking the reverse path. Okay, so that means plus with the reverse path, the integral should be equal to 0. Okay, and now you can see that a plus gamma r1 and a plus gamma r2 in the reverse direction can be broken into several such small integrals. Yeah, so I can keep doing like this. All of you agree to that? Yeah, so I can divide the area of the annulus in several parts, and then what I can see that the integrals in the intermediate lines, they are going to get cancelled. Effectively, I will be ending up with integral on the outer circle and integral on the inner circle on the opposite direction. But I'm not yet done over here. Okay, I still need to do something much little bit more. Now, why do I break these things at all? I want to break these things in such a way so that each of these segments, these are each of these closed paths that I am getting, I'm going to break them, like I'm going to arrange these smaller parts in such a way that each of them can be packed inside a circular region. Each of them I should be able to pack inside a circular region which is completely inside my domain of holomorphic. Once I have that, then I can apply closed curve theorem. Okay. So if I have this, let's say each uh, region which the way I broke it, if each of them are can be packed inside some circular region, then I know my function is holomorphic in that circular region. There I will be able to use closed curve theorem, and therefore the integrals are going to become equal to 0, and therefore in adding I am going to get this particular statement. Okay, So is this clear to you what I said?
Yes, sir.
Sorry. Okay, so the basic idea was this. Okay, so with the picture that is drawn, let me just write it down for you. So what I do, we divide the area in annulus in several parts such that each smaller closed curves can be seen inside a disk, and therefore integral along them will be 0, and once integral along them is equal to 0, if you add all of them, what you get, adding them, we get, uh, let me call it star. So we get star. So that's the basic idea, that at every place I pack each of these smaller closed paths inside a circular region. Okay, then I can apply closed curve theorem over there. Okay, so you see, do not blindly apply closed curve theorem on any holomorphic function. For example, 1 over z is holomorphic on c minus 0, but if you just imagine a closed curve over there, uh, let's say circle of radius 1, then we have seen that the integral is 2 pi 2 I pi. Okay, so in the end, what we needed, for example, if you remember rectangular theorem or triangle theorem, we really needed holomorphicity in a ball, and then on that we could prove rectangle theorem followed by integral theorem followed by closed curve theorem. So we really needed ball. Okay, so we cannot have any kind of holes in it. Okay, so here clearly there is a hole, so you need to break your integral into several sub integrals. Each of those sub integrals you need to pack them inside, or each of these sub contours you need to pack them inside a ball, and then apply your closed curve theorem. Okay, so therefore I have this one. Fine. So now that I have this, so let me quickly write down what do I get. I get that. So now what is G? G, I have already told you. Oh, did I not write? Yeah, G is this one. So I get G integral over a plus gamma 1 is same as G integral over a plus gamma R2. So therefore I get integral over a plus gamma R1 f of z divided by z minus alpha minus a plus gamma R1 f of alpha divided by z minus alpha equal to a plus gamma R2 f of z divided by z minus alpha minus a plus gamma R1 f of alpha divided by z minus alpha. So I have this. Fine. So now
R2,
I,
sir.
sorry, R2.
Last
Yeah,
term.
thank you.
Last integral.
Yeah, yeah, R2. Yeah, exactly. So now if I club the terms corresponding to f of alpha, what do I get? F of alpha times, let me write it in the other side. So what I can do, yeah, so I will take the bigger integral first. So a plus gamma r1 1 over z minus alpha minus a plus gamma r2 1 over z minus alpha is equal to integral a plus gamma r1 f of z by z minus alpha minus a plus gamma r2, sorry, yeah, f of z divided by z minus alpha. So this is what I get. Okay, fine, that's all right. And now what do I do? I need something more. Of course, exactly like we had expanded. in case of when we wrote power series expansion, we are going to do exactly that same thing. So write 1 upon z minus alpha as 1 upon z minus a minus alpha minus a. So therefore this is 1 upon z minus a into 1 by 1 minus alpha minus a divided by z minus a. Okay, fine. Now therefore this is 1 by z minus a. Remember, z is something which is on like my generally z is either here or here. Okay, so therefore clearly whatever is your corresponding to, I have this one. Okay, so I have this particular property, so accordingly I am going to use uh, like in one segment I'm going to use one part, in another segment I'm going to use another part. So I will do that carefully. Okay, so just keep an eye. So 1 over z minus a, so 1 plus alpha minus a divided by z minus a plus alpha minus a divided by z minus a squared, and so on and so forth. So this one converges uniformly for mod of alpha minus a divided by z minus a less than 1, right? So that means mod of alpha minus a less than mod of z minus a. Now where do I have this? I have this on a plus gamma r1, because on a plus gamma r1 I have z mod of z minus a is equal to r1, and r1 is strictly bigger than mod of alpha minus a. So note, on a plus gamma r1 we have mod of z minus a is equal to r1, which is strictly bigger than alpha minus a. So I can apply this particular formula on a plus gamma r1. Okay, now if I have z in a plus gamma r2, then what am I supposed to do? Let us see what am I supposed to do. On a plus gamma r2, what do I have? We have mod of z minus a is actually r2, and this is less than mod of alpha minus a, because that's how I have chosen my r1 and r2 from. Okay. So this is exactly the hypothesis that I have. So this guy is now this time less than r2 is less than mod of alpha minus 2. So we write, so this time I am going to write the same thing but in a slightly different form. I am going to write z minus alpha as a minus alpha minus a minus z. I write like this. So I take out a minus alpha common, and then I write 1 minus 1 by a minus z, a minus alpha, or I can just, yeah, I can just just transfer it. It doesn't really matter. Okay, so anyway, I need alpha minus a power n, so let me just balance it in a way. So this one will be minus of alpha minus a into 1 over 1 minus alpha minus a z minus a. Yeah, that should be fine. And therefore this is minus summation n bigger than or equal to 0, exactly like that. Alpha minus a, let me just see. Yeah, no, this should be alpha minus a power uh, uh, let me just write it clearly. 1 by alpha minus a, and here I have 1 plus alpha minus a by z minus a plus alpha minus a divided by z minus a square, and so on and so forth. So this is what I can write. This is minus summation n bigger than or equal to 1. How do I write this? Okay, I'll see. I can write this as, yeah, sorry, did I make a mistake? Is it by, yeah, sorry, here I have made a mistake. That's the problem. This is z minus a, this is alpha minus a. Z minus a, this is alpha minus a. That's what I'm thinking. This is z minus a, this is alpha minus a. Okay, let me quickly finish this. So therefore this will be n bigger than or equal to 0, z minus a power n divided by alpha minus a power n plus 1. Okay, so here of course it was the other way. So it was summation n bigger than or equal to 0, alpha minus a power n, z minus a power n plus 1. Okay, so here it's just the opposite one. Okay, so therefore what I get is that you can clearly see that now if I just consider the integrals accordingly. Okay, so now, okay, so I see it's already time, you guys have another class, so let me finish it in the next class. So next class is on Saturday because Saturday is a working Monday. So I'll finish it on in the next class. So you will see that integral coming from this part, which is on gamma a plus gamma r1, I am going to have only one contribution, which is going to be 2I pi, and all other contributions are going to be 0. And for this part, anyway, everything in z minus a, that's holomorphic. So integral coming from this part is going to give me 0. Okay, so effectively what I am going to have, I am just going to get f alpha from here, or 2I pi times f alpha, and then here from this part I am going to get my expansion. Okay, so this we will see in the next class because it's already time. Okay, so there is nothing much left in this. Okay, so I'll stop here, and in the next class I'll continue from this.